Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Back in the 1970s, and from Corvallis, Oregon, to Washington, District of Columbia, and in the 1980s, from College Park, Maryland, to Casper, Wyoming, to Los Alamos, New Mexico, United States. I was a research computational mathematician that was supercomputing across a new internet, that is a new supercomputer de facto. My parallel processed supercomputer arithmetical operations were the byproducts of the system of 9 coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations of calculus that I invented. I used those partial differential equations, called the Philip Emeagwali Equations, to more accurately model the flow of crude oil, natural gas, and injected water flowing across production oil field, such as the Niger-Delta oilfields of the southeastern region of Nigeria. My contribution to physics and geology is this. I discovered how a parallel supercomputer can be used to discover and recover otherwise elusive crude oil and natural gas. My invention of 1989 was the cover story of top mathematics publications and is used to model how crude oil, injected water, and natural gas flow from the injection wells to nearby production wells. In mathematical theory, the exact solution of any differential equation is defined across an infinite number of points in space and time. For that reason, it will take an infinite set of calculations to exactly solve a differential equation and solve it across a supercomputer that is as large and as old as the universe. It will take forever to exactly solve the numerical approximation of any differential equation. At its supercomputing core, each of my 64 binary thousand commodity off-the-shelf processors was adding and subtracting floating point numbers and calculating them at the speed of the ordinary computer that was powered by only one processor. Yet, there was a paradigm shift or a fundamental change in the technique and technology that I was using to solve grand challenge problems that is called parallel processing or supercomputing 65,536 problems at once. In the old paradigm of programming of programmable computing that began in 1946, a singular computer was used to solve the grand challenge problem of the 1940s. That tough problem was to compute the high and arching trajectories of ballistics that were tested at Aberdeen Proving Ground in Aberdeen, Maryland, and to compute those trajectories at the then unheard of speed of 5,000 additions per second. At its mathematical physics core essence, that grand challenge problem is the second law of motion of physics that was restated algebraically as the iconic formula force equals mass times acceleration, or F equals ma. That formula in turn is encoded into ordinary differential equations of calculus that govern an initial value problem that describes the trajectories of powered and guided missiles that fall under gravity. In the new paradigm of parallel programming that began on July 4, 1989, millions upon millions of processors compute together as one cohesive supercomputer that solves as many grand challenging problems and solves them via email communication across a new internet that I visualized as my new global network of processors. On the 4th of July 1989, I figured out how to send and receive answers to partial difference equations of extreme scale algebra that mathematicians called initial conditions and boundary conditions. Those intermediate answers were for my initial boundary value problems of mathematical and computational physics. The poster boy of the 20 grand challenge problems of supercomputing is the general circulation model that is used to foresee otherwise unforeseeable climatic changes. My contribution to the development of the computer made the news headlines because I discovered how to harness 1 million processors. I discovered how to use 1 million processors to simultaneously solve real-world grand challenge problems and to solve them across a new internet that is a new global network of those 1 million processors. What was newsworthy was that I discovered how to harness 64 binary thousand processors and how to do so via email messaging that traversed 1 binary million bidirectional pathways. I discovered how to chop up a grand challenge problem into 65,536 problems and how to send and receive those smaller problems to and from 64 binary thousand commodity off-the-shelf processors that were identical to each other, that were tightly coupled to each other, that shared nothing between each other. Each CPU that is the brain of the computer, that is where most calculations take place, that defined and outlined my internet, was akin to a tiny computer. My invention paved the way for the modern computer. After my invention, the vector processing computer is no longer a leading-edge supercomputer. As a result of my discovery that the fastest parallel supercomputer will always be faster than the fastest vector processing supercomputer, and after that discovery, the manufacturers of vector processing supercomputers either shut down or refocused on the newer massively parallel supercomputers. After my discovery that occurred on the 4th of July 1989, some of the 25,000 vector processing supercomputer scientists that were put out of work were retrained on parallel processing and rehired at corporations that manufacture the massively parallel supercomputer. Those vector processing supercomputer scientists had to be retrained because the new massively parallel supercomputer is a completely different animal altogether, in part because each processor had to send and receive email messages to and from nearest neighboring processors. The radically different parallel supercomputer was a revolution, not an evolution. Today, parallel processing is the unofficial shorthand for the modern supercomputer that could become the modern computer of tomorrow.
Insightful and brilliant lecture.